We will continue our discussion of chemical composition and performing composition calculations. When two fluids are mixed, mass is conserved, since mass cannot be produced or lost in mixing. Thus, mixing 20 grams of any material with 15 grams of another will always yield a mixture which has a mass of 20 grams plus 15 grams, which is equal to 30 grams. However, it is not true that volume is conserved. The volume of a mixture may differ from the sum of the volumes of the materials mixed together. The densities of fluid mixtures often are unknown. However, the density is required to perform process calculations. Density may be estimated by assuming the volume change that occurs upon mixing is small. The volume will change, but the differences are small if the two fluids are similar in terms of intermolecular interactions. To calculate density assuming volume additivity, consider mixing a mass m sub A of fluid A with a mass m sub B of fluid B. The total mass upon mixing is equal to the mass of A plus the mass of B. The volume of each pure component can be calculated from its density. The volume of A, V sub A, is equal to the mass of A divided by the density of A. The volume of B is calculated in the same manner. Assuming volume additivity, the total volume, V sub T, is the sum of the volumes of A and B. Substituting mass divided by density for the volumes of A and B yields the equation shown. Density is defined as mass divided by volume. Substituting the expression for total mass and total volume yields the result shown. This equation can be used to estimate the density of a mixture as illustrated next. Note that we can calculate the masses of A and B, MA and MB, from the total mass using the mass fractions of A and B, XA and XB, from the definition of mass fraction. MA is equal to the mass fraction of A times the total, and MB is equal to the mass fraction of B times the total mass. With these values, then, we can plug them into the equation above to calculate the density. In this example, the density of a 35% by mass solution of sulfuric acid in water is estimated assuming volume additivity. The subscript S denotes sulfuric acid, and the subscript W denotes water. The mixture is 35% by mass acid, so the mass fraction of acid is 0.35. The sum of the acid and water mass fractions must equal 1, so the mass fraction of water is 1 minus 0.35, or 0.65. Assuming we have 100 grams of the mixture, the mass of each component can be calculated by multiplying mass fraction by total mass. The sum of the calculated masses for water and acid equals 100, as expected, since we assumed the total was 100 to perform the calculations. Note the value ultimately calculated for density does not depend on the assumed total mass of the mixture. Any value could be used. An internet search, or using Wikipedia, indicates the density of the acid is 1.84 grams per centimeter cubed, while we know the density of water is 1 gram per centimeter cubed. The volume of water and acid can be calculated by dividing the mass of each component by its pure component density. Assuming volume additivity, total volume of the mixture is estimated by adding the volumes of each component. The density is calculated by dividing total mass by total volume. The actual density of a 35% by mass sulfuric acid solution is reported in the reference literature as 1.26 grams per centimeter cubed. An internet search for sulfuric acid solution density yields several sources for this value. This differs by approximately 5% from the value estimated assuming volume additivity. The actual value is higher because of strong intermolecular interactions between water and sulfuric acid that bring the molecules closer together. On occasion, you may need to convert between mass and mole fractions. The process for this conversion consists of the 5 steps shown. First, assume you have an arbitrary amount of the mixture, typically 100 grams. This is referred to as the basis for the calculation, and the final results do not depend on it. Second, calculate the mass of each component using mass fraction. Third, convert the mass of each component to moles using molecular weight. Fourth, calculate the total moles of the mixture by summing the moles of each component. And fifth, calculate the mole fraction of each component from the definition of mole fraction. Component moles divided by total moles. The process for converting mole to mass fraction follows the same steps, starting from an assumed basis of 100 moles. An example of this conversion is provided next. A mixture contains 10% ethanol, 75% ethyl acetate, and the balance acetic acid on a molar basis. What are the mass fractions of each component? Note that mole percent is equal to 100 times the mole fraction. Similarly, mass percent is 100 times mass fraction. Thus, the mole fraction of ethanol is 0.10, and the mole fraction of ethyl acetate is 0.75. The calculation of mass fraction from mole fraction is facilitated by creating a table like that shown here. This could be created in Excel, which also can be used to perform the calculations. Note that the sum of the mole percent of each component in a mixture must equal 100. This implies the sum of the mole fractions must equal 1 as indicated. The statement that the balance of the mixture is acetic acid implies it is the only other component in the mixture. While its mole percent or fraction was not provided, the sum of the mole fractions must equal 1. So subtracting the known mole fractions from 1 gives the mole fraction of acetic acid. The first 2 steps of the conversion are shown here. The basis of 100 total moles is shown. The moles of each component are calculated from the definition of mole fraction. Component moles equals mole fraction times total moles. The next 2 steps of the conversion are shown here. The molecular weight of each component is obtained from Wikipedia or an internet search. Note that Wikipedia generally is a good source of chemical information and physical property data such as density. The mass of each component is calculated from the product of moles and molecular weight. The total mass is calculated by summing the component masses. The final step of the conversion is shown here. The mass fraction of each component is calculated by dividing the component mass by the total mass. Note that the sum of the calculated mass fractions should equal 1. On occasion, you may wish to calculate a mixture's average molecular weight, the symbol M with a bar above it. 2 formulas are provided for this. The first uses mole fractions, while the second uses mass fractions. The summation sign implies that the value of the indicated quantity for each component is summed. For example, the average molecular weight is equal to the sum of the product of mole fraction and molecular weight for each component. The inverse of the average molecular weight is equal to the sum of the ratio of mass fraction to molecular weight. The value calculated for the y to x conversion example is provided. The last composition calculation covered here is the conversion between mass fraction and concentration. The procedure for doing so consists of the 6 steps shown. The first step is to either look up the density of the mixture or estimate it by assuming volume additivity. The next step is to assume a basis of 100 grams in total of the mixture. The volume of the assumed basis is calculated from the definition of density. The mass of each component in the mixture is calculated from the definition of mass fraction. The moles of each component is calculated from molecular weight. Finally, dividing the moles of each component by the volume of the basis gives concentration. The procedure for converting concentration to mass fraction is shown here. It is similar to the procedure for converting mass fraction to concentration, but starts from a basis of 100 centimeters cubed total volume instead of 100 grams total mass. An example of the mass fraction to concentration conversion is provided next. In this example, a mixture of ethanol and water contains 60% water by mass. The specific gravity of the mixture is 0.93518 relative to water at 4 centigrade. At 4 centigrade, water has a density of 1,000 kilograms per cubic meter, or 1 gram per centimeter cubed. We have been asked to calculate the concentration of ethanol in units of moles per liter. The specific gravity of the mixture is provided relative to water at 4 centigrade. From the definition of specific gravity, the density is calculated by multiplying specific gravity by the reference density. Using the known reference density of 1 gram per centimeter cubed for water at 4 centigrade, the calculated value is 0.9352 grams per centimeter cubed. Note that density in units of grams per centimeter cubed is numerically equal to specific gravity only when water at 4 centigrade is a reference. The numerical value will be different if water at 4 centigrade is not the reference. The volume of 100 grams of the mixture is calculated from the definition of density. Volume equals mass divided by density. The calculated value in centimeters cubed is converted to an equivalent value in liters with a conversion factor of 1 liter per 1,000 centimeters cubed. The mass of each component is calculated from the definition of mass fraction and the assumed basis of 100 grams of the mixture. Component mass equals the product of mass fraction and total mass. After looking up the values for molecular weight of each component, the moles of each component are calculated by dividing mass by molecular weight. The calculations are facilitated by creating the above table in Excel and performing the calculations in the spreadsheet, as discussed for X to Y calculations. Finally, the concentration of each component is calculated by dividing the moles of each component by the total volume of the mixture.